Jai Hind everyone. I Dr. Rohit Kumar Maheshwari, working as an assistant professor in the Department of Applied Science and Humanities, Ajay Kumar Garg Engineering College. I am taking a lecture on Engineering Mathematics-I. Subject code is BAS 103 and the topic of my lecture is Homogeneous Function and Euler's Theorem on Homogeneous Function. These are the content of my lecture. First one is homogeneous function, second is Euler's theorem on homogeneous theorem, deductions from Euler's theorem. In the first section, homogeneous function, I will discuss basic definition of homogeneous function and different type of homogeneous function and alternative test for homogeneous function. What is homogeneous function? A function f is said to be homogeneous function of degree or order n in x and y if it can be put in the form of x to the power n phi of y upon x or y to the power n phi of x upon y. An alternative test for function f to be homogeneous of degree n in x and y if function tx ty equal to t to the power n function of xy. Then this function is called homogeneous function of degree n. For example, if function f equals to x plus y upon root x plus root y, then this function equals to x 1 plus 1 upon y upon x upon root x 1 plus root y upon x equal to x to the power 1 by 2 phi y upon x. In the first case, we common x from numerator and root x common from denominator. So this function can be put in the form of x to the power n phi y upon x. So this function is homogeneous of degree 1 by 2 in x and y. In this case, this function can be put in the form of y to the power n by 2 and phi of y to the power n by 2 and phi of x upon y. This function can be put in the form of y to the power n phi of x upon y. So we common y from numerator and root y common from denominator. So this function is homogeneous of degree 1 by 2 in x and y. In third case, and this function can be tested by alternative test, and we put x equal to tx and y equal to ty. So function tx comma ty equal to t to the power 1 by 2 function of xy. So we can say that this function is homogeneous of degree 1 by 2 in x and y. In all these cases, this function is homogeneous of degree 1 by 2 and x and y. In this section, I will discuss Euler's theorem on homogeneous function. If u is homogeneous function of degree n in x and y, then x del u over del x plus y del u over del y equal to nu, where n is degree. Since u is homogeneous function of degree n in x and y, so it can be put in the form of u equal to x to the power n function of y upon x. So firstly, we differentiate partially with respect to x, we get del u over del x equal to n x to the power n minus 1 function of y upon x plus x to the power n f dash y upon x, and again differentiate with respect to x. So we get minus y upon x square. So it implies x del u over del x equal to n x to the power n function of y upon x minus x to the power n minus 1 y f dash y upon x. This is equation number 1. Also, we can find the partial derivative with respect to y. We get del u over del y equal to x to the power n f dash y upon x into 1 upon x. By product rule equal to, we can also find del u over del y. We get del u over del y equal to x to the power n f dash y upon x into 1 upon x. So equal to x to the power n minus 1 f dash y upon x. It implies y del u over del y equals to x to the power n minus 1 y f dash y upon x. This is equation number 1. Adding these two equations, we get x del u over del x plus y del u over del y equal to n x to the power x function of y upon x, and x to the power n function y upon x, which is equal to u. So we get x del u over del x plus y del u over del y equal to nu. Not Euler's theorem. Not Euler's theorem can be extended to a homogeneous function of any number of variable. Thus, if u is a homogeneous function of degree n in x, y and z, then x del u over del x plus y del u over del y plus z del u over del z equal to nu. So this theorem can be extended any number of variable. Not if u is homogeneous function of degree n in x and y, then x square del 2 u over del x square plus 2xy del 2 u over del x del y plus y square del 2 u over del y square equal to n into n minus 1 into u. In the second section, deduction from Euler's theorem. If u is not a homogeneous function, so it can be put in the another form, that is this form: function of u equal to v of x y, where v is a homogeneous function in x and y of degree n, then x del u over del x plus y del u over del y equals to n function of u over f dash u, and x square del 2 u over del x square plus 2xy del 2 u over del x del y plus y square del 2 u over del y square equals to phi of u into phi dash u minus 1, where phi of u equal to n f of u over f dash u. So this is deduction from Euler's theorem. In this problem, we will verify the Euler's theorem for the function u equal to x to the power 1 by 2 plus y to the power 1 by 2 x to the power n plus y to the power n. And second question is u equal to sin inverse x upon y plus tan inverse y upon x. So in the first problem, given u equal to x to the power 1 by 2 plus y to the power 1 by 2 x to the power n plus y to the power n. This is equation number 1. Firstly, we will check this function is homogeneous or not. So this function can be checked by the t-test. So we put x equal to tx and y equal to ty. We get t to the power 1 by 2 x to the power 1 by 2 plus y to the power 1 by 2 into t to the power n x to the power n plus y to the power n equals to t to the power n plus 1 by 2 into u x y. That is, this function is homogeneous function of degree n plus 1 by 2 in x and y. By Euler's theorem, we get x del u over del x plus y del u over del y equals to n plus 1 by 2 into u by Euler's theorem. For verification, differentiating first partially with respect to x, we get del u over del x equals to 1 by 2 x to the power minus 1 by 2 x to the power n plus y to the power n plus n x to the power n minus 1 x to the power 1 by 2 plus y to the power 1 by 2 by product rule. It implies x del u over del x equals to 1 by 2 x to the power 1 by 2 into x to the power n plus y to the power n plus n x to the power n x to the power 1 by 2 plus y to the power 1 by 2. Similarly, we can find the partial derivative with respect to y. We get del u over del y equals to 1 by 2 y to the power minus 1 by 2 x to the power n plus y to the power n plus n y to the power n minus 1 x to the power 1 by 2 plus y to the power 1 by 2 by product rule. It implies y del u over del y equals to 1 by 2 y to the power 1 by 2 y to the power 1 by 2 into x to the power n plus y to the power n plus n y to the power n into x to the power 1 by 2 plus y to the power 1 by 2. So adding these equations, we get x del u over del x plus y del u over del y equals to 1 by 2 x to the power 1 by 2 plus y to the power 1 by 2 into x to the power n plus y to the power n plus n into x to the power n plus y to the power n x to the power 1 by 2 plus y to the power 1 by 2, which is equals to this function. Hence, Euler's theorem is verified. Hence, Euler's theorem is verified. In this problem, firstly we check this function is homogeneous or not. Again, we put x equal to tx and y equal to ty. We get t to the power 0, u x to the power y. It implies u is homogeneous function of degree 0 in x and y. Hence, by Euler's theorem, we get x del u over del x plus y del u over del y equals to 0. From equation 1, del u over del x equals to 1 upon root 1 minus x square upon y square into 1 upon y plus 1 upon 1 plus y square upon x square into minus 1 upon x y upon x square equals to 1 upon root y square minus x square minus y upon x square plus y square. So it implies x del u over del x equal to x root y square minus x square minus xy upon x square plus y square. Similarly, we find the partial derivative with respect to y. We get del u over del y equals to x y root y square minus x square plus x upon x square plus y square. So it implies y del u over del y equals to minus x upon root y square minus x square plus xy upon x square plus y square. Adding these equations, we get x del u over del x plus y del u over del y equals to 0, which is same as equation 2. Hence, the Euler's theorem is verified. In this problem, if u equal to tan inverse x cube plus y cube upon x minus y, prove that x del u over del x plus y del u over del y equals to sin 2u, and x square del 2u over del x square plus 2xy del 2u over del x del y plus y square del 2u over del y square equals to sin 4u minus sin 2u equals to 2 cos 3u sin u. Here, u is not a homogeneous function, but it can be put in the form of function of u equals to v of xy. So, u is not a homogeneous function. So, let tan u equal to x cube plus y cube upon x minus y, which is equal to function of xy. Now, this function is homogeneous or not? So, we put x equal to tx and y equal to ty. We get t square function of xy. It means this function is homogeneous function of degree n equal to 2. By Euler's theorem, we have x del u over del x. So, x del over del x, del tan x, del tan u over del x plus y del tan u over del y equals to 2 tan u. Del over del x tan u. So, it implies del over del u tan u into del u over del x. So, x sec square u del u over del x, because derivative of tan u sec square u. So, x sec square u del u over del x plus y sec square u del u over del y equal to 2 tan u. So, it implies x del u over del x plus y del u over del y equals to 2 sin u over cos u into cos square u. So, it implies 2 sin u cos u equal to sin 2u. So, this is verified. In the second case, here phi u equal to sin 2u and phi dash u equals to 2 cos 2u. By deduction from Euler's theorem, we know that x square del 2u over del x square plus 2xy del 2u over del x del y plus y square del 2u over del y square equal to phi of u into phi dash u minus 1. Phi dash u sin 2u, phi dash u, 2 cos 2u, minus 1 sin 4u minus sin 2u, which is equals to 2 cos 3u into sin u. So this part can be proved, by directly Euler's theorem, deduction from Euler's theorem. For example, x del u over del x plus y del u over del y equal to n function of u over f dash u. This is deduction from Euler's theorem. So it implies x del u over del x plus y del u over del y equal to 2. F of u is 10u over sec square u, which is equal to 2 sin u cos u, which is equal to 2 sin 2u, which is equals to 2 sin 2u. So by directly using deductions from Euler's theorem. In the next problem, if u equal to log x to the power 4 plus y to the power 4 upon x plus y, show that x del u over del x plus y del u over del y equals to 3. Here u is not a homogeneous function, so this function can be put in the form of f of u equal to v of xy. So it implies e to the power u equal to log x to the power 4 plus y to the power 4 upon x plus y. Here f of u equal to e to the power u and v of xy equal to x to the power 4 plus y to the power 4 upon x plus y. And this function is homogeneous function. This function is homogeneous function of degree n equal to 3. Hence, by Euler's theorem, we have x del over del x e to the power u plus y del e to the power u over del y equals to 3 e to the power u, and u x e to the power u del u over del x plus y e to the power u del u over del y equals to e to the power u, e to the power common, so it implies x del u over del x plus y del u over del y equals to 3. And this part can be directly solved by deduction from Euler's theorem. Deduction from Euler's theorem. This part can directly solve by deduction from Euler's theorem. X del u over del x plus y del u over del y equal to n f of u over f dash u equals to 3 e to the power u over, and derivative of e to the power u is e to the power u equals to 3. Hence proof. Thank you.